Okay, so now we will start with a new topic. Okay, so today what we will do, so we will design a sequential comparator. Okay, so what is a sequential comparator? I will explain it here. Okay,
Professor, you're not sharing screen.
okay. So now I will now share my screen. So now the topic of today's lecture is a sequential comparator. And what is a sequential comparator? We are comparing two numbers A and B. Got it or not got it? So let's assume we want to compare. So the objective. What is our objective? So our objective is to design a sequential comparator. So our objective is to design a sequential comparator. And what is a sequential comparator? So we are comparing. So our objective is to design a sequential. We are comparing. We are comparing two numbers A and B. Okay. So let's assume we have two numbers A and B are n bits. So these are n. It's an n bit number and b is also an n bit number. So let's say we have an a, and a will start from a n minus 1, a n minus 2, and blah 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 until ai, until blah 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 until a1 and a0. And then we have another number bn minus 1, bn minus 2, and blah 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 until bi, and blah 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 until b1 and b0. So this is a0, sorry. So we want to compare one bit by one bit. Okay. So can you see what is the range of I? So in this example, the range of I will be from 0 to I smaller or equal to n minus 1. This is clear or not clear? This clear? Please answer me because you know
It's clear, Professor.
Yeah.
this clear. Okay. So what we are going to do now, we are comparing each bit one by one. So basically, we are comparing AI and BI. We are comparing each bit one by one. And I will explain this with an example. So let's assume that we want to compare these numbers, and let's assume we have this we are different, there are different time instances. So let's assume this is time t0, this is time t1, and this is time. Please remember, in any sequential system, we take a decision at the edge of the clock. So let's assume this is my clock, this is my clock now. So let's assume this is my t1, t0, this is t1, this is t2, and blah blah blah. So these are the time instants. So we have like what I'm going to do. So now I'm writing this time. So these are different time instants: t0, t3, t4, t5, t6, t7. So these are different times. Got it? Okay. So let's assume we have these times. So we have t0, we have t1, we have t0. Okay. So the time goes in there in this direction, not in the opposite. So t2, t3, t4, and t5, and t6, and t7, and blah blah blah. So let's assume we are comparing two quantities a and b. So this is my a. Now this is my b now. Okay, and let's assume n is equal to 8. N is equal to 8. So n is equal to 8. So let's assume if you are comparing two quantities 0, 0, 1, 1, 0, 1, 0, 1, and b is also 0, 0, 1, 1, 0, 1, 0, 1. Okay, for this example, are these quantities equal or not? Can you tell me? Yes or no?
Yes.
Yes. So
Yes.
it means that in this case, equal will be 1, LT will be 1, 0, and GT will be 0. Got it or not got it? So now take another scenario. So now I'm using a different color for this. So please remember, so the different colors are for different scenarios. So let's assume we have an A, and now I'm using a red color, and B. And let's assume the value is actually, can you see here? This is 1, 0, 1, 1, 0, 1, okay, and 0, 0, 1, 1, 0, 1, 1, 1, 0. Now, if you look at this operation, so can you tell me A is greater than B or what? Can you even answer? Can yes?
Yeah, A is greater than B.
So can in the red thing we can say, oh yeah, A is greater than B. Yes, but now let's assume if we say now we can say we are okay now okay if we say that A is greater than B, let's assume if I'm starting at from only t0. Okay, so let's assume if my say, so let's assume there are different states. So there are different states. So I call these some states. I call these states. There are some states. The states are three states: equal, E stand for equal, G stand for GT, and L stand for less. You got it or not got it? Okay. Now the thing is, we are getting these bits serially one by one. So now these are my states now. These are my states. These are my states. And let's assume if I'm looking at the LSB side, if I'm looking at the LSB, okay, AI is equal to BI or not. So basically, this is a time t0. Now I'm at time t0. AI is equal to BI. What should be my state now? I don't know the future. I'm not starting at time t0. Can you tell me what should be my state now? Anyone may answer?
Zero.
Equal.
No, equal. Who said zero? Who said zero?
Javier.
No, no, it should not. It's not be. It means actually AI at this point at t0 AI is one and BI is one. So it means that they are equal. Am I got or not? This is clear or not clear?
Okay.
Then I move to a time t1. If I move to time t1, it means AI is zero and BI is zero. So are they equal or not? Yes or no?
Yes.
Yes,
Yes. Now
Professor.
I'm comparing two bits. Okay. Now at this point of time I'm comparing one. So it means I'm comparing one with one. But at time two I'm comparing two bits. I'm comparing 0 1 with 0 1 because now there are two bits. And also depends on the previous state. So now the state will be equal. Got it or not got it? Any question? At time t3,
Professor,
how many bits I'm comparing? At time t3.
Professor, I have a question.
Yes, please go ahead.
If they're both the same, then do we move to the next state or what?
Yeah, we move to the next state because the state is changing at each time.
Okay.
Okay, now please just look at logically. Do you know I want to make a logical argument, and we can do that. What's going now at time t3? Now basically the previous state is equal. So now the three bits are 101 and 101. Are they equal or not? Yes or no?
Yes.
Yes.
Equal. Now I'm moving time t4 because in time t4 now we are comparing not three bits. We are comparing how many bits? Four bits. And now we are comparing 0101 and then we are comparing 1101. Got it or not got it? So in this case, what should be now the state?
A less than B.
Yes, so I can say L because equal is this is A is equal to B, G A is greater than B, and L is equal to A less than B. So this is my motion. Got it or not got it? Any question? This is clear or not clear? Okay, now if I move to if I move to the other bits, so basically now in this case now we are comparing five bits. So what will be the answer? Can anyone answer? Yes,
Greater than.
it will be greater than B. Okay, now this is now a more complicated thing. Now if I'm at time t6, now I'm comparing 1 and 1. So what should be my next state? Anyone may answer.
Greater than.
Yes, it will still be greater because though AI is equal to BI, but based on our previous result, it will still be greater. You got it or not got it? Because it's based on the previous state. And now if I go to the next state, so basically it's AI is equal to, it means it will still be greater, G. But let's assume if we have another number. So let's assume if we have another number. So now I'm going to do, so we have another bit. Let's assume this is another bit. It's 0 and this is 1. So now in this case, if we compare all of the bits, it will move to which state? Anyone may answer.
Less than.
Less
Less.
than.
Less.
You got it? I got it. So now you need to know the logical argument that I want to make. So what we are going to do? So basically, we have, and the state will change. This state will change based, and then we are comparing. We are not comparing all bits at once. We are not comparing all bits at once. We are only comparing one bit at a time. And each bit is comparing. Okay, so basically at time t0 we are comparing. Okay, at time t0 we are comparing a0 and b0. And in time t1, we are comparing a1 and b1, but we are also a1 and b1, but we also consider the previous state. And time t2, we are comparing a2 and b2, but it also depends on the previous state. You got it or not got it? Any question? Is clear or not clear? If
Clear,
I'm not
Professor.
hearing an answer, it's not a good sign. Please.
Clear, Professor.
Okay. Now I want to see the number of students who are like just listening. There are only 13 students. Okay. Okay, now think of this comparator. And definitely we want to design this comparator. So we want to compare AI and BI. So this is my comparator now. So can you see? Okay, now possibly, it means that there should be three states now in the in the system, so basically there should be three states. The first state is called as equal state. The second state is called as LT state, and the third state is called as GT state. Any question? This is clear or not clear? So there are three states in the system. Okay, please remember. And basically there should be three states in the system. We call this as equal state, this we call this an LT state, and we call this an GT state. Okay, now let's assume if we have a reset. So reset will initialize the system to some known state. This is actually reset is will initialize the system to an equal state. And then we are comparing AI, and please remember, we have comparing AI and BI. There are four possible values of AI and BI: 0, 0, 0, 1, 1, 0, and 1, 1. Got it or not got it? Okay, now assume that I'm in the, okay, let's assume when the system is reset, it is initialized to the equal state. And when it is initialized to the equal state, so let's assume the first possible value is 0, 0. So 0, 0, AI is 0 and BI is 0. So, and I'm in the equal state. Where should I go? Equal state, should I go to LT or should I go to GT? Anyone may answer, please go ahead. 0, 0.
Stay in the equal
We
state.
stay
Very
in
good.
equal.
Very good. We stay in the equal state. Okay, now can you tell me, this is a Mealy machine or a Moore machine? Yes.
Mealy.
Anyone may answer?
Mealy. Mealy.
Huh?
Mealy.
Mealy.
Why Mealy?
Because the output is at the edge.
Who said it's
No,
the input?
wait.
AI and BI are the
Oh,
input.
yeah, never mind. Yeah, never mind.
So this is actually a Moore machine.
Moore machine.
It's a Moore machine. So we are designing it to use a Moore. So 0, 0, it will stay as I said. Okay, 0, 1.
Wait, Professor,
Zero.
what's the difference again?
Again, how many times, you know, why you are not listening to your previous lectures? Please, I would recommend. Remember, we have on the Mealy machine, we have inputs on the left hand side and outputs on the right hand side on the edge. But here we have only inputs. We don't have any outputs. Output is inside the state.
Okay.
And this equal is actually your output.
Okay.
You got it or not got it? So basically, remember, how many times did I, if you remember all of my stuff, and I also gave you an example. Remember, this was an example. So these are inputs on the left hand side, output are on the right hand side. So this is a Mealy machine. This is a Moore machine. Only inputs on one. Remember or no? Now the problem is that
Yes, I remember.
yeah. So the problem is that when you come into this, you don't remember, you don't look into all the other thing, and all of the topics that I'm teaching is based on the previous topics. And I would suggest you, please, I would suggest everyone to at least look into the previous lecture. It will be help you for. It will be better. Okay. Now let's assume 0, 1. Where should I go? 0, 1. LT or GT?
LT.
LT.
LT, very good. 1, 0.
GT.
GT. 1, 1.
EQ.
Equal. It will stay in equal state. Because 1, 1, they are equal. This is clear or not clear?
Clear.
Any question?
Professor?
Clear or not clear?
Professor?
Yes, please go ahead.
For the Moore machine, the output only depended on the current state, and then the Mealy, it's...
Yes, the output depends on the current state. So can you see inside equal state? So basically, we can have three outputs for it. So basically, okay, now I will explain it. No problem. So now let's assume if you are in the equal state. So there can be three outputs: G, L, and E. G stands for greater, L stands for less, and equal. So in equal state, so basically in equal states, if the output is inside the state, so G, L, E in E, so this will be actually 1, 0, 0. No, sorry. G, L, and E. E is 1, 0, 0, 1. Here L is 1, 0, 1, 0. Here G is 1, 1, 0, 0. You got it or not got it? Any question?
And got
Clear or not clear?
clear.
Clear? So in equal state, E is 1, in GT state, G is 1, and in LT state, L is 1. Clear or not clear?
Clear, Professor.
Okay, now assume that we are in the
Professor?
L state. Yes, please go ahead. Yes, very good.
Why do
Very
we
good.
use 3 bits to represent the state?
It's not, Thomas, you're Thomas, yes?
Yeah, why do we use 3 bits to represent the state? There's only 3
Basically,
different
it
states
is
here.
not the state. It is actually the output. For the state,
Oh,
we can.
okay.
You're not getting my point now.
Yeah, it's Moore. I forgot.
It's a Moore. So it's a Moore. So basically, it is not the state assignment. It is actually the output assignment. So the output assignment is totally different from the state assignment. I hope I answered your question.
Yeah, I got it. Thank you.
So this is the output assignment, not the state assignment. I will explain the state assignment later on. Can you give me some time? Then I will explain everything. Got it or not got it?
Got it.
Okay. Now let's assume I'm now in the GT state. Let's assume I'm now in the GT state. I'm now in the GT state, and I'm now using a different color. So basically, I'm now using the green color now. 0 0. What should I do? 0 0. I'm in GT state. 0 0. Where should I go? Anyone may answer. If you want to get some bonus points.
Equal.
No. Because if I move to the GT states, it means that the previous bits are unequal. So in the previous bits are unequal. Please remember here. Now you're again, you missed the logic here that I explained it here. Basically, even if they are equal, if the previous state is G, it will remain in the G state. You're not getting my point.
It
Yeah,
will
I got
retain.
it.
You got it or not got it?
Yeah, I got it.
So basically, this is very good. I know that if even, please remember, if you are answering me wrong, it is better that you at least answer me, because it will improve your concepts. Because my objective here is to improve your concept, not to memorize, not to think based on the logical argument. You got it or not got it? Please answer, even if your answer is incorrect. If your answer is incorrect, so you will not repeat this mistake in your final. That's my objective. Okay, now let's assume if I'm in the GT state, and let's assume if the input is 0 0, where should I go? Yes, anyone may answer?
Retain. So if
It
it's
will retain.
GT,
Yes,
it will
it will
be
retain.
GT.
GT.
And if it's 0 1, 0 1, please remember, now we are going to the MSB side. So
Less
0 1,
than.
so now, huh?
If it's 0 1, it'll be less than.
Yes, it will go to
Yeah.
S less than 0 1, because now we are considering the MSB side. So the MSB of B is 1. So remember, if the MSB is 1, it will ignore all of the previous state. Got it or not got it? Any question? Clear? Because the weight of the MSB is greater than the sum of all of the weights of the LSB side, based considering the binary numbers. Remember? Okay. Now let's assume I'm in the GT state, and if this is 1 0, where should I go?
GT.
Stays in
I will
GT.
stay in the GT state. And 1 1
Stays in
GT.
Stays
is
in
the GT
GT.
state. Yeah, it's the current state GT state. Now I'm going to the LST state, and I'm now using a different color. I'm now using a blue color. 0 0. Where should I go?
LT.
LT. LT. 0 1.
GT.
No, 0 1. Still AI is smaller than BI.
Oh, sorry. Yeah. LT.
1 0.
GT.
Now the MSB is
G.
greater. It will go to GT. And 1 1. We are in the LT state. Now the MSB is
LT.
1 1. So it is based on the previous cut. Then
LT.
it stays in LT. I hope I got it or not got it?
Got it.
Any question? Clear? Now we have the state diagram. What should be my next step? Anyone may answer.
State
Transition
State
table.
transition table.
Yes, state transition. Very good. Now this is the good spirit. Very good, very good. So now we can see here. So now we have this diagram, and we go there. So we minimize this. This is just the so we draw the state transition table. And please remember, to do that, so we need two things. We need this thing, and we also need this thing. Why we need this thing? We did need this because this is a Moore diagram. So this is the block diagram of a Moore. Got it or not got it? Clear or not clear?
Clear.
Okay, now please look at here. Now what we are going to do, so now we are going to draw and please remember the color coding. Whenever I use the color coding, so you are always, so please remember, so we have, now please look at here. Please remember the color coding. ST is for red color. Okay, so now I can start with the design, and then I can say, okay, my ST is red color. So my ST is red color, which is my current state. My input is the blue color. Please look at the color coding here. My input is blue color. So my input is actually, and please remember, if you remember all of these notions, so you blue color. And then we have the next state, ST plus 1, which is which color? At least you can give me, please. Which color?
Green.
ST plus
Green.
1. and the output yt, and I'm not going to explain the yt because I will explain it later on, but this is now. Yeah, so can you see here? So now we can say here, so now we start with the zero thing. So basically how many states are here? So basically we have three states: equal, 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 and equal. This is the first state. Why I'm making it four, I will explain it. Because if you look at here, the inputs, the input xt, so there are two inputs. So basically these inputs are actually a and b. This is actually a and b. You got it or not got it? So this is A and B.
Yeah.
Now we have the first state equal. What is my next state? Anyone may answer. So the next state is LT, 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 and LT. And the next state is actually what? Help me.
GT.
GT, GT, and GT. Got it or not got it? And then we have the inputs A, B. So if you look at the input A, B, so there are four combinations: 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, and 1, 1. And then we need to draw the next state. And based on the diagram, if you look at here, so we know the next state, which is actually the green color. So basically, I'm now it equal 0, 0. It will go to as equal. 1, 1. It will go to equal. Please recall 0, 0 equal, 1, 1 equal. And 0, 1, 0, 1 is here. So 0, 1 it goes to LT, and 1, 0 it go to GT. Now I'm in LT. Please remember, if I'm in LT and if they are equal, they will stay in LT. LT, it here, it will stays in LT. It's here, it stays in GT. 1, 1, it stays in GT. Got it or not got it? If they are equal and the current state is so is there. Okay, now let's assume if we have LT, we have an LT and it's 0, 1. 0, 1 stays in LT, and 1, 0 it goes to GT. And again we have GT, we have 0, 1, it goes to LT and GT. Got it or not got it? So now we have filled the table. What is my next step? Anyone man? My next step. Quick, 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 quick. Please go ahead. Yes.
We assign the binary values to the states.
Yes. And please
And
remember,
then-
Thomas, I'm now going to answer your question now. Basically, now Thomas, you said that we are doing 3 bits. So these 3 bits are not these 3 bits which are inside. They are actually the output. Got it or not got it? So this is actually now 0, 0, 0, 0, 0, 0, and 0, 0. This is the state assignment: 0, 1, 0, 1, 0, 1, and 0, 1, and then 1, 0, 1, 0, 1, 0, 1, 0. Any question? Clear or not clear?
Clear.
Okay. Now can you see here? Please look at for the equal. I'm going 0, 0, 0, 0 equal. So basically, I'm not going to equal and make it 0, 0. LT. Now I'm using another color for this. So I'm now using a black color. So basically, LT is 0, 1. So this is 0, 1. So this is LT black one. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Got it or not got it? And now for the GT, I'm now using another color. So now basically, let's assume I'm making this color. So this is GT is 1, 0. So GT is 1, 0, 1, 0, 1, 0, 1, 0. Any question? Clear or not clear?
Clear.
Okay, now please remember. Now please remember. Whenever I sort, how many flip flops are we needed? So in this case, how many flip flops are there? Anyone? How many flip flops? How many flip flops? Yes,
2.
2 flip flops.
2.
And please remember, if you look at this flip flop and now look at this diagram, since we have 2 flip flops, so this is my ST. ST is actually the output of the state memory, and since it is the output of the state memory, so we can say, we can say this is the output of the state memory, so we can call it as Q1 and Q0. Got it or not got it? Clear or not clear?
Clear.
Now in ST plus 1, which is the input to the D flip flop, I can call it what? D1 and D0. This is clear or not clear? So basically ST plus 1 is actually my what? D1 and D0. And ST is actually what? Anyone may answer, please. Yes.
Q1, Q0.
Q1 and D0. Is clear or not clear?
Clear.
Okay. Now, please remember, even if we have the flip flop, it can have 0, 0, 0, 1, 1, 0, but okay, there may also be possible that there is a state which is called as 1, 1. So let's assume if there is a state of 1, 1. Got it or not got it? So in the state of 1, 1, so we ignore A and B, and we also ignore the output because these are don't care. Don't care. Why we are using don't care? Don't care are used to for logic minimization. Any question? Any question? Should I clear? Clear or not clear?
Clear.
Okay. What I'm going to do now, I'm going to copy and paste, as most of the students do it, and in your what you can see in your chat GPT or in your exams, you know that. Okay. So what I'm going to do, so I'm going to do it here. What I'm going to do, please remember, now I'm not using any colors. I'm not using any color. I'm not just directly use because I don't have any time. So I just copy and paste. I'm not doing the copy and paste. So I can have Q1 and Q0. Then we have an A and B. And then we have T1 and D0. So this is actually 0 0 0 0 0 0 0 0, then 0 1 0 1 0 1 0 1, then we have 1 0 1 0 1 0 and 1 0, and then we have 1 1. Okay, and then we have 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1, and this is XX. Got it? Now D1 is XX. So basically the output is D1 is 0 0 0, so 0 0 0 1 0 1, then 1 0, then 0 0, then 0 1, then 0 1 1 0 0 1 1 0 0 1 1 0 and 1 0. These are the same thing as this thing. These are the same thing as this. Any question? Clear or not clear? Clear or not
Clear.
clear? These are the same thing as this.
Yes, clear.
Yeah, now what we can do? Very good. Thank you for, and because if you're replying me, it gives me energy. Okay, so what I'm going to do? So basically, look at here. So this is actually 0 1 2 3 4 5 6 7 8 9 10 11, and then 12 13 14 and 15. This literally because they don't get 12 13 and 14. So can I see how can I find the expression for D1? Can anyone tell me what is the expression for D1? Anyone? Sigma M of what? Help me, quick, help me, quick.
Sigma M of 3, 6,
No, D1
8,
2 2 2 2
2, 6, 8, 10,
2
11.
6. Then what?
and then
8, 10,
sigma
11.
D,
8 10
sigma D,
and 11, and plus sigma D of what? Help me.
12 to 15.
You got it or not got it? And this may be the question in exam. If I give you this question in exam, I may say, okay, find the expression for D1 and for the expression for the state memory. For the expression for the state memory. So you can will find the expression for D1 and D0. Got it or not got it? What is the expression for D0? Anyone may answer? Yes. What is the expression for
Sigma
D0?
Sigma
M.
1,
1,
4, 5, 7,
7,
8,
8.
and then plus sigma
Not
D
8,
of
yeah, it's 9.
10 to 15.
Yeah, 9. 12, 13, 14, and 15. Got it? Got it or not got it?
Got it.
Any question? So what is my next step? What should be my next step? Next step.
We draw the circuit diagram.
But for that circuit diagram, we need an expression.
K-map, minimization.
K
Oh,
map.
sorry, yeah, K-map.
How can we draw circuit diagram without having an expression? We
Yeah,
cannot draw.
my
We
bad.
cannot draw until we have an expression. Got it or not got it? So we need a K map. We need a K map to derive the expression, which is the minimized expression. It can be a SOP expression, or it can be a POS expression. It can be an end or logic, or in logic unmixed expression, or with the logic sharing. You all know, already know all of these concepts, and we have discussed it before. Any question? Clear or not clear?
Clear.
Clear.
Okay, what we are going to do? So basically, what I'm going to do? So basically, then we draw the K-map. So basically, these are the K-maps, and basically based on the K-maps, we have this expression. So based on this K-map, so we have this expression. So this is actually please remember this based on this K-maps. We have this K-map. Please do all these things. These are already done. So based on the K-map, this is the expression for D1 and D0. Clear or not clear? So I'm not going to do that because you already know it. Can you see here for D1? For D1, how many ones are there? 1, 2, 3, 4, 5, and 4 don't care. In D1, 1, 2, 3, 4, 5, and 4 don't care. And same for D0. Got it or not got it? This clear or not clear?
Clear.
Yes.
Clear? Okay. Now when we derive the expression for D1, so this is my D1. This is the expression for here. This is the expression for D1. This is clear or not clear? Any question?
Clear.
Okay, now for that we also need another thing, because we also have this thing control C and then control P, and I copy and paste as you do it in your ChatGPT based exams. So basically I'm going, it's a good joke, but it's a good joke, yes. Okay, so now if you look at here, please remember we said it there. So now we have the current state. So in the current state we have this what you do. So this is the current state. This is actually Q1 and Q0. Am I right or not? ST plus 1 is what? Help me. ST plus 1 is what?
D1 and D0.
D1 and D0. You got it or not got it? So basically, if you look at here, so now we have, and now look at here that I'm now going to draw the diagram. So now this is the whole diagram. This is my next state logic. And in this state logic, the input is ST, which is actually Q1 and Q0. and the other input is xt, which is A and B. You got it or not got it? So basically, if you look at here, and the output of this next state logic is D1 and D0. So this is D1 and this is D0. Can you see here D1 is now a function of Q1, Q0, and A and B, and similarly D0 is also the function of this. If you look at here, so what is the expression for D1? So this is the expression for D1. This is actually Q1, so we got it. So this is Q1 dot. So we need, so basically what I'm doing, so basically what I'm going to do, so I'm going to draw and then you do it like this. So basically what we do, so this is Q1 dot A plus B bar. So A, this is A, and then plus B bar. A plus B bar, and then we replace product. It is done with Q1. This is Q1 A plus B bar, and then plus A B bar. So plus A B bar, A B bar. So A, we can say it here, A, and then B bar. B bar is coming from here. This A B bar, and if we or all of both them, if we both or of them, so we got what? T1. You got it or not got it? Any question? This clear or not clear?
Clear.
Clear? And similarly, we can draw the circuit diagram for D0. So basically, for the circuit diagram for D0, we can draw it from here. So I'm not going to draw the whole diagram because this is D0. So you can draw this diagram something, you draw it from here and then you get from here. And since we have D1 and D0, how many flip flops we need? We need 2 flip flops. So basically, we need 2 flip flops. This is the first flip flop. This is actually the D, and then actually this is the output. Then we have the clock, and then we have the reset. Then we have another clock. Then it goes to the D. Then we have the Q, and we have another clock. And please remember, this output is now what? Q1, and this output is now feedback here. And now this is Q0, and this Q0 is feedback here. This is clear or not clear?
Clear.
Yes, clear.
Any question? And now please remember, now we have an output logic. The output logic. And please remember, there are 3 outputs. Remember, one is E, one is L, and one is G. Remember or not? Any question?
Yes.
Yes. Okay, now this is E, then this is L, and now this is G. Is clear or not clear? Okay, how now I'm going to derive these expressions, and please, I need your attention. Because why I need your attention? Because this is very intelligent way of designing the things that I need your attention. Okay, now if I say, now I'm going to have, so let's assume if I'm in the equal state. So the equal state is 0, 0, remember? Any question? So Q1 is what? Any question? So this is Q1 and Q0. So basically I can say, one minute. I just, so basically, so let's assume we have 4 possible values of Q1 and Q0. 0, 0, 0, 0 means I am now in the equal state. 0, 1, I am now in the LT state. And 1, 0, I am now in which state? GT state. Is it clear or not clear? Any question? Clear? Because this is based on the assignment. Yeah, 0, 0, 0, 1, 1, 0. Any question?
Clear.
This clear? Okay, now let me say that it is 0, 0, 0, 1 or 1, 0. This is Q1 and Q0, 0. Okay, now we have 3 outputs. Remember G, L, and E. What is the value of G, L, and E in this example? Anyone may answer.
The first one, 0, 0, 1.
Very good. The second one,
0,
yes.
0, 1, 0.
0, 1, 0.
0. Very good. And then
1, 0, 0.
I'm very pleased. Very good. Very good. Now, if you look at please look at here. Now, look at here. Just look at this diagram. Can you see this L? L is 1 if Q1 is, so L is the same thing as Q1. Can I say L is equal to Q0? Am I saying right or not? So L is the same thing. Got it or not got it?
Yes.
So L is the same thing as Q0. This clear or not clear?
Clear.
Yes.
Okay. What about G?
Q1.
And
Q1.
G is the same thing as Q1. This is intelligent design or not? Can you see the design? Got it or not got it?
Yes.
Got it.
Okay. Now can you see where should this L? Now we have the output logic. We have an output logic. So output logic. So basically, LT is same thing as Q0. We need LT is same L is same thing as Q0. So Q0 is directly connected to L, and G is the same thing as clear or not clear? Any question?
Clear.
Okay. Now
Clear.
what about E? What about E?
It's XNOR. Q1 XNOR Q0.
No. It is actually Q1 bar. Can I see? It will E will be
Oh,
1.
yeah.
Q1 bar, Q0 bar. Can I write here? Any question?
Yes.
Can I apply the De Morgan's theorem? Yes or no?
Yes.
Yes.
So if you go for here, so basically what we do, so basically this is can you see here? So now I can use another color. I can use a color of this black color. So we can say here, and then this is go from here, and this will go from here. Any question? This is now my output logic. Any question?
Professor, why do we do it this way and not represent E, L, G as like two outputs, like 2 bits?
No, that yes, we can also, that is actually the compact representation.
Okay.
But this is actually called as the, like, let's assume if we have, like, let's assume if we have three traffic light signals, the red, green, and blue, red, green, and yellow, like the traffic light. So you need, like, if it's E is one, so it means it's giving its equal or something like. So basically, just like to for the user to clear it what's going on. Let's say if you have three LEDs, one LED for E, one LED for L, one LED for G. You didn't get my point.
I got it. I got it. So in the
Regarding
question,
this is just like from the theoretical perspective, from the user perspective. It all depends on the scenario that how we can design a comparator. Any question?
they'll specify how many bits is the output.
Definitely. In the question, everything will be described. What are the inputs? What are the outputs? Design it using it as a Moore machine, or using it as a Mealy machine, using it D flip flop or T flip flop. There's a lot of, like, design space. The design space is huge. Any question?
Clear.
Professor, why don't we consider 1 as input?
Because the thing is, not the total number of possible states are only 3, because there can be only 3 possible outcomes, and that is called as undefined state. And since basically, why do we have a reset mechanism? Reset is used to initialize the system to unknown state. You got it or not got it? Because there are only 3 possible states.
Oh,
There is no, you got it. You didn't get my point.
I got it, Professor. Thank you.
Any other question? Very good. I'm very happy. I'm very happy today. Any question? Should we proceed?
Sure.
That's good.
Professor.
I really like the interaction today. I'm very happy today. Okay, so basically, if you do that, so this is how it works. This is okay. Now if you look at here, now just this is actually GT and LT bar. This is EQ basically. Okay, now I use a NOR gate, but what they do, they you use Q1 0 bar, because on the flip flop we have Q1 bar and Q0 bar, and they make it. This thing is called as which logic? This thing, this gate. Anyone may answer?
The
Which logic is
gate
this?
and gate.
AND gate, but output logic. Got it or not got it? Which logic is this? The yellow one.
NSL logic,
NSL logic. What is this thingy? Anyone tell? Can you tell me this one?
state memory.
Stack
Current.
memory. And this is actually D1 and D0 are the ST plus 1, and Q1 and Q0 are ST. You got it or not got it? Because this is all you need to you need to memorize all these things. These are the general, like the concepts. Any question? Mm-hmm. Any question? This is clear or not clear?
Clear.
Okay. Okay, so now we have the unused state, and so now what we are going to do. So now basically we want to design. We did it with the comparator, and now we can see here what's this thingy. So we want to design a binary counter. What is a binary counter? It counts from 0 to 7. So let's assume this is t0. So the state is t0, 0, 0, 0. Then the next state is 0, 0, 1. Then the next state is 0, 1, 0. Then 0, 1, 1, 1, 0, 0. And then it goes back to 0, 0, 0. There is no input to the circuit. So this is just like a self-running counter. Can you see here? This is the state diagram here. And it's a self-running. No inputs and no output. The state is actually your outputs. Is it a Mealy machine or a Moore machine? Anyone will
Moore.
answer? Yes, a Moore machine. There's nothing, no input, nothing, everything. The system is making a transition on like in clock edge, and this is the things. What should be my next step now? What should be my next step now? We have the state diagram. The state transition
draw
table.
the
We do the state transition table. Can you see? So basically, what do we do? No, the next step is to assign the states. So 0, 0, S0 means 0, 0, 0, S1, 0, 0, 1. So the binary assignment. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, and 1, 0. You got it or not got it? Any question? Clear or not
Clear.
clear? Okay, now if you look at here, so if you look at here, this is very simple. This is very simple to draw. So basically, if my current state is S0, my next state is S1. If my current state is S1, my next state is S2. If my current state is S2, my next state is S3. And my current state is S7, my next state becomes S0 back. It goes back to, got it or not got it? So S7, it goes to. Any question? This is clear or not clear?
Clear.
Okay, now if you look at this counter, so basically this counter, so what can you see here? So now basically, what is D2? So D2 is sigma M of what? Anyone may answer?
3, 4, 5, 6.
0, 1, 2, 3, 4, 5, 6. What about D1?
1, 2, 5, 6.
1, 2, 5, 6. What about D0?
0, 2, 5, and 6.
No, 0 to 4, 6. On alternate 0, 2, 4, and 6. Got it? Got it? Yes? Okay, so then we draw this thingy, and then basically definitely we draw the state diagram. So if you go for the state diagram, so this is the state diagram. So we got this expression. This expression we got it from the chem maps. So this expression is from the chem map. And please remember, this, if you look at here, this D2, this is which expression? SOP expression. Then this D2 is also we do it, and now if you look at here, we got an expression for D2. Which expression is this? The mixed gate. Remember?
next. Yes.
And then we have for the D1, we have Q1 and Q0. This is also a mixed gate approach. Got it or not got it?
Got it.
Any question? Clear?
Clear.
And now please look at here. What is D0? Look at here. How do we derive from D0? If you look at D0, and this is my D0, D0 is actually the inverse of Q0. So basically, if D0 is 1, it depends on Q2. So it is actually D0 is the same thing as Q2 bar. Got it or not got it? So if 0 is, sorry, no, sir, not, sorry, I'm sorry. D2. D2, what's the expression, sorry. D0 is Q0 bar. Control Z. So D0 is the inverse of Q0. If it is 1, it's 0, 0, 1. So it means, got it or not got it? Any question? So D0 is the same thing as Q0 bar. And we can find it from the table. Any question? This is clear or not clear?
Clear.
Okay, so this is how we derive the expression. And please remember, we have the same thingy. There is this diagram. I don't know. Oh, yeah, this diagram. So we have the next state logic. The NSL. This is ST. In ST, actually, there are now three flip flops. Got it or not got it? There are three flip flops. So these three flip flops are Q2, Q1, and Q0. And then we have the thing. This is actually D2, D1, and D0. So this is actually D2, D1, and D0. Then we have Q2, Q1, and Q0. So we have Q2, Q1, and Q0. And please remember, this there is no input xt. There is no input xt. So what is D0? D0 is Q0 bar. So basically D0 is the same thing as inverter. Got it or not got it? Any question? And what
Clear.
is D1?
Clear.
Q1 or Q0.
And similarly, you can find the expression for D2. So basically here we have three flip flops. So and the output of this is actually, can you see here? This is my Q2, this is my Q1, and this is my Q0, and this Q2 feedback is here, and Q1 is coming here, and Q0 is coming. Any question? Clear or not clear?
Clear.
Clear? And then you can also find the expression for D2. So D2 is basically some blocks here, so we go for there, and I'm not going to explain, give that. You can do it from here. Any question?
Clear.
Okay, now so if you look at here, this is the final diagram. So can you see here? This is actually the output is here. This is the whole output. This is the whole output, and this is the whole output. So basically, can you see here? Okay, basically, when I see, I was saying I was using an inverter, but since we have Q0 bar, so we are using a bar here. Got it or not got it? Any question? Instead of using an inverter, we can directly see the output because every flip flop has two outputs, Q0 and Q0 bar. So if there is Q0 bar, so we do not need an inverter here. Clear or not clear? Any question?
Clear.
Okay, what is this thingy? Anyone may help? What is this thingy? Which logic is this?
Mixed.
Yes, mixed, but NSL. Got it or not got it? This
Got
is your
it.
current state and this is your next state. Any question? This is clear or not clear?
Yes.
Okay, now there is another problem. And that problem is more complicated. Okay, got it or not got it? So this is another problem. Please remember, until now, until now, until now, we have covered some FSM based examples. We have covered some FSM based examples. Okay, we did a vending machine example. And that vending machine example was done using melee based. Remember? Yes or no?
Yes.
Then we did a sequence detector. and we did it using Mealy and Murray machine. Got it or not got it?
Yes.
Then after that we did what? Help me. Comparator. Sequential comparator. And we did it using Mealy or Murray?
More.
Murray. After that we did a counter and we did it in Murray. For all of these problems, we use which flip-flop? We used
D.
D.
the flip-flop. So now what we are going to design now. In the next example, we will use in the next example. So in the next example, we will design a circuit, sequential circuit using T flip-flop. Clear? Any question? How? Let's see. Let's see. So what is the problem specification? So the problem specification, we are going to design. So we are going to design a 2-bit up-down counter. We are going to design a 2-bit up-down counter. So we are going to design a 2-bit up-down counter. Okay, so we have two inputs, enable and out. Okay, please remember it's a 2-bit counter. So the possible state can be 0 0 0 1 1 0 and 1 1. These are the possible states because this is a counter, it counts. So it counts from 0 to 3 because it's a 2-bit counter. So this actually it 0 1 2 and 3. You got it or not got it? So now there are two first the other inputs. There are two other inputs. So the other inputs are E. If E is equal to 0, if E is equal to 0, the counter remain the same state. So same state. And E is equal to 1, there are two possible values. Got it? If then we have another signal U. If U is 1, it will count up. And if U is equal to 0, it will count down. So this is now the specification of a counter. And how we can now design the counter? Okay, now so we have 4 states. S0, S1, S2, and S3. Okay, if there is a reset, what should we do? Anyone may answer. Reset.
S0.
S0.
Okay, now I am in state S0. Okay, there are two inputs. Please remember there are two inputs, E and U. 0 0 0 1 1 0 1 1. So these are 4 states. 0 0 means same state. 0 1 same state. 1 0 1 0 is means down.
Next.
1 1 up. Any question? Clear or not clear?
Clear.
Okay, now let's assume I'm in a 0 and it's 0 0. Where should I go? 0 0.
S0.
0 1.
S0.
Yes. 1 0.
S0 still.
Down. So what is minus 1? But minus 1 is not there. Where should we go?
S3.
S3.
Is it still
1 1.
S1.
S1 up.
S1.
Now I'm in S1. I'm now using a red color. 0 0. Same. 0 1. Same. 1 0. Down. Where should I go?
S0.
S0.
1 1.
S2.
S2. Now I'm in S2. I'm now using a black color. 0 0.
S2.
0 1.
S2.
1 0.
S1.
1 1.
S3.
Okay. Now I'm in S3. 0 0 will stay here. 0 1 will stay here. 1 0 which is down. 1 1 up.
S0.
Got it or not got it?
Got it.
Any question? What should be my next step now? Next step.
State transition table.
State transition table. Simple. The same. Believe me, if you know the problem at hand, so whenever you know the problem, so basically you will do all the things will be very easy for you.
Professor, this is More.
Yes, this is Mure, because there is nothing output, because this E and U are the inputs. Is there any sense? So this is all Mure. And now please remember, we are only going to design it using T flip flop, not D flip flop. Got it? How we will do it? I'll explain it later on. Is it clear or not clear? Any question?
Clear.
Okay. What should be my, and now please, since it's a Moore machine, so it's a Moore machine, so it will be something like this. So we are copying it here. We are pasting it here. Please remember, since we have, this is a Moore machine, so since we have this thingy, so basically what we are going to do, so now we can say we have two flip-flops, we have Q1 and Q0 here. The next state will be actually, okay, now please remember, we should have T1 and T0, not D1 and D0. Why? Because we want to design it using T flip-flop. Any question? And what is the input? So the input is now E
EU.
and U. Any question? Should we proceed?
Yes.
Okay. Now what we are going to do? Okay. Now what we are going to do? This is very important now. What we are going to do? So now basically we draw the state transition table, and then we go for the state transition table. So this is my thing, state transition table. So this is actually ST, and this is my input XT, and ST is actually E and U. Then we have ST plus 1. The same thing, the same color coding, the same thing, ST plus 1. And there are 4 states. So basically, can you see here? There are 4 states. So you can see here S0, 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 and S0. Then S1, 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 and S1. Then we have S2, 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 and S2. Then we have S3, 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 and S3. Got it or not got it? So this is how it works. So basically now if you go for the thing is for the inputs. So these are the 4 states: 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. And now my ST plus 1 is based on the thing. So basically if we go for the ST plus 1, so basically if it's, please remember, E 0 0 or 0 1, it's same S0 S0, same S1 S1, same S2 S2, same S3 S3. Okay. Now if you go for this thingy, this is actually up, S3, up, no, down, sorry, down.
It's down. Yeah.
So S0 is S3,
S3 only.
S0 down, S1 down, S2. Got it or not got it? Any question?
Clear.
Clear? And then 1 1 up. S0 become S1, S1 become S2, S2 become S3, and S3 become S0. Okay, now we do the state assignment. So when we do the state assignment, so this is 0 0, 0 1 0 1 0 1 0 1 1 0 1 0 1 0 1 0 1 1 1 1 1 1 1 1. Got it? Got it. And now this is actually, can you see here, 0 0 0 0 0 0 0 0. Then S1 0 1 0 1 0 1 0 1. S2 1 0 1 0 1 0. Where is S2? 1 0. S3 is 1 1 1 1 1 1 and 1 1. Clear or not clear? Any question?
Clear.
Clear. Okay, now this is very important. Okay, if you are going to design it using D flip flop, so what will be my ST plus 1? Anyone may answer.
D1, D0.
So this will be D1 and D0. Got it or not got it? Any question? But now we are going to design it using D flip flop or T flip flop?
T.
T flip flop. Now, how to design with T flip flop? I am now going to give it in my next slide. Okay, now what I'm going to do, I'm going to copy and paste. Okay, so basically what this is HT. So basically I'm using the same color. Please remember, I'm not using any other color. So I'm using the same color because I don't have any time. So basically what you have ST, then you have E and U, and then you have D1 and D0. So this is actually 0 0 0 0 0 0 0 0. Then we have 0 1 0 1 0 1 and 0 1. Then you have 1 0 1 0 1 0 and 1 0. Then we have 1 1 1 1 1 1 and 1 1. So we have 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. But now if you look at D1 and D0, this is actually 0 0. Then 0 0 1 1 0 1 0 1 0 1 0 0 1 0 1 0 1 0 0 1. Then we have 1 1 1 1 1 1 1 0 and 0. Clear or not clear? Any question?
Clear.
Okay. But we have now, if you want to design it using D1 and D0, we can directly design it. We can make an expression for D1. What is D1? D1 is sigma M and blah blah blah. So we can expand D1. But now our objective is to design it using D flip flop or T flip flop.
T.
T flip flop. Okay. Now for T flip flop, we have two things. So please remember, this is very important. So basically, this is actually now Q1 and Q0. And now I'm the same thing. This is now my D1 and D0. Clear? Okay. Now for that we need to do the excitation table. So for that excitation table, so this is the excitation table for T flip flop. This is not the excitation table for T flip flop. Remember, this is. Please remember, this QT is the same thing as QT. This is actually same thing as QT, and this QT plus 1 is actually the next state, and this is actually DT. Got it or not got it? Because the next state is D. Any question? Is clear or not clear? Okay, now we need to do. Okay, now if they are same, so please look at here. If they are same, T is equal to 0. And if they are different, T is what? Help me.
1.
This clear or not clear?
Clear.
Okay, now can you see here? Now please look at here. Now we are going to do it here. Now we need to go for, now we are comparing Q0 and D0. So now I want to find for T0. So 0 0. So both of them are 0 0 0. 0 0 0. 0 1. They are different. 1. 0 1 different. 1. Again, this one and this one. 1 1. Okay. Q0 is 0 and D0 is 1. Both are same or different? Yes.
Same.
Same. What should we do T0?
0.
0. 1 1.
0.
0.
0.
1 0. 1
1.
1. 0 0. 0 0. 1 1. And then 1 1 0. 1 1 0. 1 0 1. 1 0 1. Any question? Similarly, you can find it for T1. So for T1, we need to compare Q1 and D1. And Q1 and D1, so 0 0 0. 0 0 0. 0 0 0 1 1. 0 0 0. You got it or not got it? Any question? This clear or not clear?
Clear.
Clear.
And then 0 0 0 0 0 1 and then 1 1 1 1. Now this is 1 1 same 0 1 1 0 1 0 1 1 1 0 1 1 0 1 1 0 1 1 0 1 0 1. Any question?
0.
Any question?
Clear.
Okay, now what is T1 now? Can you tell me what is T1 now? T1 is now sigma m of what? 2 7 10
15.
and 15. And similarly, you can find an expression for T0. And if you go for all these things, we do all these things. Please remember, for T1 there are 4 ones. There's 4 1. And basically we got this expression for T1 and T0. Any question? So now if you go for here, these are the expression for T1 and T0, and we use it using the chem map. So please remember, this is again thing. We derive this expression from chem map. So we have the next state logic. So now we have an NSL. In this NSL, you have the inputs E and U. E and U are the inputs. This is my XT. And then we have the inputs Q1 and Q0, which is the red color. And the output of this is now not D1 and D0 because we want to design it using T flip-flop. So the output of this is actually, which is ST plus 1. Please remember this is ST. This is actually T1 and this is T0. And since we have a T flip-flop, so we have, instead of D flip-flop, we have T flip-flop, then we have a clock, then we have a reset. And then we have another flip-flop, which is actually T flip-flop, then we have a clock, and then we have a reset. And then the output of this thing is actually, Q1, and Q1 is feedback here. And the output of this is Q0, and Q0 is feedback here. Any question? Clear or not clear?
Clear.
Okay, now what is the expression for got it or not got it? Any question?
Professor, you cut out.
What?
You cut out when you said, what is the expression for?
Okay, what is the expression for T0?
T0 is E.
E. Simple. T0 is the same thing as E. What's the problem? What is T1? E dot and AND gate. Q0 exclusive NOR. Q0 exclusive NOR U. Got it or not got it? And this is T1. Any question?
Clear.
No.
There
Sorry.
should be an AND.
Yes. Exclusive NOR. And this is actually E.
And E.
This one. Got it or not got it? Clear?
Got it.
Yes. Clear.
T1. Any question? Clear or not clear?
Clear.
So this is the whole diagram of designing using T flip-flop. Any question? Any question? So now it will go. So I'm now going to a little bit like, this is with the what I did, but this is like some kind of an animation from here. So you go here. So basically we have four state, S0, S1, and S2. So if it's 1 1, we go up. S0 from S0 to S1, from S1 to S2, S2 to S3, and S3 to 0. 1 0, we go down, we go backward. Here we go forward, here we go backward. And if E is 0 0 or 0 1, we go on the same state. And reset will initialize the system to the known state, which is actually in this case in S0. We draw the state transition table, and then it's called as the thing. So for T flip flop, we need to use the excitation table. We need to use the excitation table for the T flip flop, and based on the excitation table, we derive the expression for T1 and T0 based on the we derive the expression for T1 and T0. So we derive the expression for T1 and T0. We derive the expression for T1 and T0 based on the previous thing. Any question?
Professor,
Mm-hmm.
in the diagram, why didn't you add the output logic?
Because this is a counter. And in the counter, we
Oh,
don't know the outer. Basically, the state by itself is your output. So can you see here by the state? So basically in here, the state is your output. So this Q1 and Q0 is so it means that since it is a counter, so if it is 0 0, it means that it is S0. If it is 0 1, it means it is S1. If it is 1 0, it means it is S2. If it is 1 1, it means it's S3. Got it or not got it? So actually, the state is actually your output.
okay.
You got it or not got it? Any question?
Got it.
Okay, now let's assume if you want to have like we have four states and we use four different colors for this state. Let's say we want to have four different colors for this state. State 0, S1, S2, and S2. What should we need to do here? Anyone may answer?
Professor,
We
can
want
you
four, let's we need four LEDs. And this LED should be on if it is in state S0. This should be on with state S1. This should be on in state S2. And this should run with state S3. What we need?
We need output logic.
Output logic, but for that output logic, we need what structure? 2 to 4 decoder. Remember? So this will be
Yeah.
on 0 0. This will be on 0 1. This will be on 1 0. This is on 1 1. You got it or not got it? Any question?
Why do we need? Oh, never mind. I got it.
Because in 2 to 4 decoder, only one output will be enabled at a time. And this is the decoder. So it means that the output will be either 0001 or 0010 or 0100 or 1000. I hope I answered your question.
Yeah, I got it.
You got it? This is all conceptual thingy, because digital system is all about the concept. It's all about the concept. It how you have a lot of structure, hardware structure. You have multiplexer, you have encoder, you have decoder, you have priority encoder, you have the adder, you have the subtractor, but you need to know when to use what structure. For some structure, even you don't need any logic. You need to say, okay, I can use this hardware structure. Any question?
Clear.
Clear? Okay, I have uploaded now your marks on the island. Okay.